Part 2. Distribute data. For a successful technology, reality must take precedence over poly relation. For nature cannot be fooled. Richard Feynman, Royal Commission Report 1986. In part 1 of these books, we discuss aspects of data system that apply when data is stored on a single machine. Now, in part 2, we move up a level and ask what happens if multiple machines are involved in the storage and retrieval of data. There are various reasons why you might want to distribute data across multiple machines. Scalability. If your data volume, read load, or write load grows bigger than a single machine can handle, you can potentially spread the load across multiple machines. Fault tolerance, high availability. If your application needs to continue working even in one machine, or several machines, or the network, or an entire data center goes down, you can use multiple machines to give you redundancy. When one fails, another one can take over. Latency. If you have users around the world, you might want to have servers at various locations worldwide so that each user can be served from a data center that is geographically close to them. That avoids the users having to wait for networks packets to travel halfway around the world. Scaling to higher load. If all you need is to scale to higher load, the simplest approach is to buy a more powerful machine, sometimes called vertical scaling or scaling up. Many CPUs, many RAM chips, and many disks can be joined together under one operating system, and a fast interconnect allows any CPU to access any part of the memory or disk in this kind of shared memory architecture. All the components can be treated as a single machine. The problem with the shared memory approach is that the costs grow faster than the linearly. A machine with twice as many CPUs, twice as much RAM, and twice as much disk capacity has another typical cost significantly more than twice as much. And due to bottlenecks, a machine twice the size cannot necessarily handle twice the load. A shared memory architecture may offer limited fault tolerance. High-end machines have hot swappable components. You can replace disks, memory modules, and even CPUs without shutting down the machine, but it's definitely limited to a single geographical location. Another approach is the shared disk architecture, which uses several machines with an independent CPU and RAM, but stores data on an array of disks that is shared between the machines, which are connected via fast network. This architecture is used for some data warehousing workloads, but connect contention and the overhead of locking limit the scalability of the shared disk approach. Shared node architectures. By contrast, shared nothing architectures, sometimes called horizontal scaling or scaling out, have gained a lot of popularities. In this approach, each machine or virtual machine running the database software is called a node. Each node uses its CPU, RAM, and disk independently. Any coordination between nodes is done at the software level using a conventional network. No special hardware is required by a sharing nothing system, so you can use whatever machine has the best price performance ratio. Can potentially distribute data across multiple geographic regions and thus reduce latency for users and potentially be able to survive the loss on an entire data center. With cloud deployment or virtual machines, you don't need to be operating at Google scale. Even for small companies, a multi-region distributed architectures is now feasible. In this part of the book, we focus on shared nothing architectures, not because they are necessarily the best choice for every use case, but rather because they require the most caution from you, the application's developer. If your data is distributed across multiple nodes, you need to be aware of the constraints and trade-offs that occur in such a distributed system. The database cannot magically hide this from you. While a distributed shared nothing architecture has many advantages, it usually also incurs additional complexity for applications and sometimes limit the expressiveness of the data models you can use in some cases. A simple single-threaded program can perform significantly better than a cluster with over 100 CPU cores. On the other hand, shared nothing systems can be very powerful. The next few chapters go into details on the issues that arise when data is distributed. Replication versus partitioning. There are two common ways data is distributed across multiple nodes. Replication, keeping a copy of the same data on several different nodes, potentially in different locations. Replication provides redundancy. If some nodes are unavailable, the data can still be served from the remaining nodes. Replication can also help improve performance. We discussed replication in Chapter 5. Partitioning. Splitting a big data set into small subsets called partitions so that different partitions can be assigned different nodes, also known as sharding. We discussed partitioning in Chapter 6. There are separate mechanisms, but they often go hand in hand, as illustrated in Figure 2.1. With an understanding of those concepts, we can discuss the difficult trade-off that you need to make in a distributed system. We will discuss transactions in Chapter 7, as that will help you understand all the main things that can go wrong in a data system and what you can do about them. We'll conclude this part of the book by discussing the fundamental limitation of distributed system in Chapter 8 and 9. Later, in part 3 of the book, we will discuss how we can take several potential distributed data stores and integrate them into a large system, satisfying the needs of a complex application. But first, let's talk about distributed data.